Hello, participants. We are going to start for this lecture.
Good afternoon, everyone.
Saurabh,
Am I audible, sir?
yeah, you are audible. And dear participant, this lecture series is sponsored by Electronic Devices Worldwide Private Limited, Sigma Weld, and Mr. Saurabh is representing. Today, he will present for his company. I request Mr. Saurabh to start for the presentation.
Yes, sir.
Saurabh, we are host now. Okay.
Yes, sir.
Your host now. Just run your the short film.
Okay, sir.
Yeah.
Good afternoon, everyone. I am Saurabh Sharma, Digital Marketing Executive at Electronic Devices Worldwide Private Limited. In the behalf of Nimesh Chinoy, Marketing Director of Sigma Weld, I'm presenting this thing.
सौरभ स्टार्टिंग में जाओ और स्टार्ट में जा और पहले जा गो टू स्टार्ट और स्टार्टिंग में जाओ या नाउ यू कैन स्टार्ट द फिल्म सौरभ साउंड नहीं आ रहा तुम्हारा सौरभ साउंड नहीं है
Sound नहीं आ रहा, sir?
साउंड नहीं है तुम्हारा
Yes, sir, madam.
ये स्पीकर ऑन दो नीचे का फिल्म वापस प्ले करो हाँ, ये नीचे का हाँ बंद ओपन करो मुझे नो साउंड सौरभ साउंड नहीं है तेरा
Sound मेरे यहाँ आ रहा, sir.
गया तेरा साउंड काम कर रहे साउंड नहीं प्ले करो सिस्टम सौरभ क्या हो गया तेरा साउंड को तो सर हो गया. हाँ सौरभ.
Yes, sir. Thank you, sir.
ओके नाउ अभी स्टॉप शेयरिंग करो.
Done, sir.
Okay, हो गया. Dear participant, now we'll go to main lectures. Hello Saurabh, can you listen to me? Hello Saurabh,
Sir, I'm here.
can you listen to me?
Yes, sir.
Yeah, the dear participant, now we'll go to for the main lecture. I will introduce our speakers, Mr. Chu. He's Marketing Development Manager, Southeast Asia for the Nickel Institute and is based in Singapore. He is responsible for market development activities in Asian markets outside Japan and China, executing projects, developing opportunities, and managing partners' relations in the region. Prior to joining the Nickel Institute in 2018, he worked for Thyssen Edelson and then for Bentler, where he undertook for the past 25 years a number of special assignments in Singapore and the Asian Pacific region, including establishing organization and joint ventures. A Swiss national, he studied marketing, economics, and commerce in Switzerland. Now I request Mr. Joe for taking over the session. Joe, sir.
Thank you very much for the lovely introduction.
Yes.
If you can give me the host right so I can quickly share my screen, I would quickly like to introduce the Nickel Institute as well, IMOA, the key sponsors of this event as well.
Your host now. Yes, sir. You can share the screen.
Okay, yes, I have seen that now. Desktop 2.
Yes.
Okay, I hope you all can see it now.
Yes, sir, we can see.
Perfect. So, firstly, a warm welcome to everyone. Please allow me to quickly introduce the Nickel Institute and as well IMOA. The Nickel Institute is a global association of the leading nickel producers. We are promoting the proper use of nickel in various applications. We support markets for new and existing applications, including stainless steel, and where we as well do risk management and socioeconomic benefits in public policy and regulation. So as you all know, nickel plays a vital role in over 75% of stainless steel. So our headquarters is located in Toronto, whereas our science division, NIPERA, is in the US, in Durham. And the Brussels office is our European Center of Excellence, mainly for public policy and sustainability and communication. Then we have two subsidiaries. One is located in Singapore and Brisbane. So the offices in China and Japan are taking care of their own markets. The International Molybdenum Association, in short IMOA, is as well a global non-profit trade organization representing most of the molybdenum industry. It promotes the properties and sustainable benefits of molybdenum, a key alloying element in stainless steel and nickel-based alloys, enhancing corrosion resistance in various modern applications. And now to the most important part. Gives me great pleasure to introduce Gary Coates to you, who most of you already know from previous talks. He's our technical manager in the Nickel Institute and sits in Toronto. Gary is a metallurgical engineer who has worked in the stainless steel and nickel alloy industry for almost 50 years. The last 25 with the Nickel Institute. He has worked with many different end-use industry and with fabricators to ensure quality fabrication and long life of equipment. He is actively involved with many professional societies in the corrosion, welding, metals, and mining industries. He has made many presentations on all aspects of use of stainless steel and nickel alloys. Gary is a professional engineer registered in Ontario, Canada. And now I would like to hand over the floor to you, Gary. And
Thank
everybody
you, Jörg.
enjoy the talk.
Yeah, thank you. And yeah, looking forward to this talk. If I could get to share.
Yes, now we are the host. Please start.
Yeah. Thank you. Let's see. Here we go. Great.
Yep, perfect.
Yeah. So today's topic is about weld cladding, and we're going to talk about stainless steel and nickel alloy weld cladding here. There we go. So this is part 5 of a 6-part series over 7 months. You can see the different topics that we've talked about, and the 6th part, the final one, will be held by Dr. Graham Sussex on weld corrosion, and that is an extremely important part of using the stainless steel nickel alloys. Is you want to avoid corrosion, and it is easy to have corrosion where you don't expect it. So make sure you sign up for that session there. So this is today's agenda. We're going to have some general comments. We'll talk a little bit about different types of cladding, because weld cladding isn't the only one, very short part. Dilution is probably the key consideration when it comes to weld overlay. We'll talk about processes and other considerations. A special little session on strip cladding, which is relatively new, a couple slides on inspection, and then conclusions and time for questions. So what is cladding? Essentially 2 or more layers of different materials that are somehow attached to each other. Sometimes we call it composite materials. In this webinar, we're going to primarily talk about where it is 2 different metals metallurgically bonded together. And here, just a common example of a stainless steel pot, a high quality one, where you have, actually in this case, 3 different materials. You have type 304 for food contact surfaces, ideal for that, for the interior and exterior for easy cleaning and hygiene. You have aluminum or even copper for the high rate of thermal transfer. And if you're using induction heating, you want the bottom part to be ferromagnetic. So a ferritic stainless steel is used there. Why do we do that? Well, there's so many different ways of advantages to do a clad, depending on what you want to do. Corrosion resistance, of course, is the main one. Strength, mechanical properties. You might use one material that's very, very strong for one side, and you want corrosion resistance on the other side. Thermal conductivity, weight saving sometimes, ferromagnetism, either for or lack of ferromagnetism, wear properties, electrical conductivity. But a lot of the cases, economics is, of course, the major factor here. And the idea is that if we use cladding, in many cases, it is to reduce the cost. Now, in the case of the pot, no, it wasn't. It was done for create a superior product, something that is the pot heats more uniformly when you have that aluminum core. So let's talk about economics. There is an assumption that a lot of people make that says, well, if it's clad, if you have stainless steel on one side, carbon steel on the other side, it's going to be less expensive than solid stainless steel. Well, that's not always true. And it depends on a lot of factors. And I just list a few here. The quantity needed. If you need a small quantity, well, it may not be less expensive. The relative cost of the two materials, the cladding process used, the thicknesses of the two materials. Obviously, if you want 3 millimeter of one material and 3 millimeter of another material, the total cost may be more than if you use solid material. With clad, you have a lot more testing involved, a non-destructive examination. You may have to test the bond strength. You might have to do special mechanical tests to make sure that it is suitable for the application. And corrosion, if you do a heat treatment, you might want to make sure that the corrosion properties have not deteriorated through the heat treatment. You might need special procedures for hot or cold forming so you don't tear the bond between the two materials, and special procedures for welding. So it's not a given that solid material is going to be more expensive than clad material. So in this webinar, we're going to talk mostly about cladding for corrosion resistance. And we talk about a corrosion resistant alloy or CRA layer on a piece of less expensive, perhaps higher strength material. So the top is a smaller, thinner layer of the corrosion resistant alloy. And we say the backing material is the thicker material, the less expensive material. So I'm going to make a few general comments here about possible materials, considering all the different cladding methods, not just the weld clad, because not all these are possible. There is that you can use different materials, plain carbon steels, high carbon steels, low alloy steels, chrome moly steels, quench and tempered steels. For their stainless steels of all families can be used, whether it's austenitic, ferritic, duplex, etc. Nickel alloys of all families, including the nickel copper alloys, and not with particularly welded clad, but titanium, zirconium, niobium, tantalum, all these special materials can be done by certain cladding methods. And we get, as we saw with the pot, alloys of aluminum and copper can be done, and emphasize not all combinations are possible by all cladding processes. And we'll look at that. So let's move on to the types and methods of cladding. It's important to understand that there are different types of cladding, and we talk about metallurgically and fully bonded, and that's the ones I'm going to be talking about, and weld clad falls under that category. Partially metallurgically bonded, and if you do a sheet lining, you line a tank with a thin layer of stainless, that we call partially metallurgically bonded because you're welding it in certain spots, but it's not totally bonded. Mechanically bonded is a good example of that is a thermal spray. It's not thermal spray, does not metallurgically bond the thermal sprayed material to the backing material. It works in many cases, but not always. And then there are some line products with minimal or no bonding at all. But we're going to only talk about the metallurgically and fully bonded materials. And those can be, there's 5 examples of that. Weld overlay, of course, is what we're going to be talking about here. I'm going to briefly mention about hot roll bonded and explosion bonded material because each of these methods has their advantages and disadvantages. And of course, I'm not going to talk about additive manufacturing, but that's also one of the more interesting areas under development. Of course, with additive manufacturing, it's very similar to weld overlay, except the whole piece is a weld material. And you can do transition layers. There you go from one material to a second material with additive manufacturing. A lot of work is going on in that area. And I really suggest to young engineers that are just graduating or have a few years of experience under the belt, that's an area that is really going to develop rapidly over the next few years. And then there's hot isostatic pressing. You can do clad materials as well as solid materials, but I'm not going to talk about those, the last two processes. So let's talk about hot roll bonded material. And this is a very simplified production scheme. I've left out a few of the steps, but just so you know how it works, you on the left there, you make a sandwich. So you have a backing material, a CRA layer, another CRA layer. These are all plates or sheets, and then a more backing material. You actually weld it up, suck out any air that might be there, and then you actually, at a conventional rolling mill, you heat the slab up and then roll it to the final thickness. You do a heat treatment, and then you eventually separate the two plates. You have a separating compound in between that doesn't allow the materials to fuse together, and then you have your quality control step. Well, this method is suitable for large quantities of clad material. They have a long delivery time, depends on what it is, but 3 months, 4 months, 6 months can even happen there. You do need to test for the bond quality and the strength. Is it fully bonded over its whole area, or has an area not bonded properly? And what is the strength of that bond? This by clad method, it must be heat treated. And then to do that, you have to choose a temperature that is suitable for both the backing material and the CRA layer. And usually there's some differences in what is ideal for both. And so you have a compromised temperature, and then you say, well, what is the effect on the corrosion resistance if that is what you're using it for? You have to be very careful with hot and cold forming, that you don't, in that operation, you don't separate the two layers. And of course, weld repair, if you need to do weld repair, it's really done in the same way that you would do a weld overlay. The second major method is explosion bonded, and essentially you have your backing material on the bottom, you have a compound on top of that, and then you have your CRA layer on top of that, and then you put your explosive on top of that, and then you get a big bang explosion there, and that will do essentially a pressure weld into the two materials. And the cross section on the right there shows that if it's properly done, you get a really, really good bond there. So it is a very popular way of cladding. There's no heat involved in it. You might think, okay, with the explosion, you get heat. Well, there's really essentially no heat involved. Advantage of this is shorter delivery time. If you can get both plates in stock, you're not changing the thickness, so you need the exact thickness you're after there. You can only do flat shapes, although they can be formed afterwards, of course, made into pipe or a head or whatever. One of the key factors, you don't need to anneal them after, but you usually do a stress relief. As you can imagine, there's a lot of stresses involved in these in this process. And I know in talking to various explosive cladders that the stress relieving is a proprietary thing. You really can't get out of them exactly what they do, what temperature they actually stress relieve at. And it is one of the secrets, one of the know-how components of making clad. And each combination of material will require usually slightly different stress relieving temperature. So Another good advantage is the metal combinations that are not easily weldable can be made. For example, titanium and aluminum can be bonded with carbon steel, and the pot that we looked at the very beginning slides, that is done by explosive cladding. There are a few alloys that you don't want to explosion clad. The nickel molybdenum Hastelloy B type alloys, they tend to crack because of the high stresses involved. And know-how is very important, the cladder. And there's a lot of cladders saying, and I've come across it many times where they say, oh yeah, we can do that. And then they try it and say, oh, I guess we can't do that. So know-how is very important there. And just we'll talk about each of these factors more a little later, but with weld overlay, just as a quick comparison, you do it in your fabrication shop. There are specialist companies that can that specialize in weld overlay. You can do a small job quickly. You know, somebody wants you need it done in 8 hours. If it's a small job, you probably can do it in 8 hours. And it's relatively quick for larger jobs too. So it's that is probably the number one reason for doing weld overlay. You can do shapes. You can weld clad ahead because of course welding can be done out of position too. So that is a major advantage. Most often, no annealing is required or even wanting to do that. We'll talk about that more. You might want to do a stress relief in some cases. Only alloys that are weldable, so you can't do titanium on top of carbon steel, for example. So they have to be weldable to each other. And we'll talk about the weld metal being slightly different composition than the wrought material, whereas with the other two methods, you're using wrought material. That occasionally is a factor. And you have to consider dilution of the base metal, and that's what we'll talk about now. So dilution, as definition, is the percentage of the base metal that goes into the weld deposit when we're talking about a weld overlay. So, for example, I'm going to take a case where we want the end user wants a minimum of a 304L stainless steel composition on the weld overlay, and you want to do it with a single pass weld. Most often you don't, but we're taking that here using 309L, which is the filler metal that you normally would use if you're welding stainless to carbon steel. You want the actual chemical composition, the main elements there of the carbon steel and the 309L, and we'll show them here. So in the carbon steel, essentially of the three that we're concerned about here, it's only carbon, and I'm just taking a figure here, 0.15, and the stainless steel 309L weld wire, low carbon, high chrome, high nickel. So if you then say, okay, I can do a weld process that has only 5%, oh, sorry, there's at the bottom is the 304L composition. I didn't indicate the maximum chromium and nickel there, but we'll talk about that shortly. But if we do a weld with 5% dilution, which is really not easy to do or almost impossible to do, you could see that we can actually meet the carbon content is less than 030 max, and you meet the minimum chrome and nickel contents there. Now that's above the 304L composition limit for chrome and nickel, but in many cases that is acceptable depending on how the end user has specified it. If we do 10% dilution, a weld process that has 10%, you can see that we just exceeded the carbon content. That may or may not have any significance depending on the application. And again, the chrome and nickel are actually high, the chrome above the um, limit for 304L itself, but usually acceptable, and the nickel is actually into the area where it is within specification. 15% we're getting more dilution, more iron into it, so the chrome and nickel are getting lower, still acceptable. Carbon is getting a little higher, 20% dilution, higher carbon, and here both the chromium and the nickel are actually within the limits of 304L. And if we do 30% dilution, all of a sudden we have too low chromium content. So it isn't, definitely not 304L minimum composition there. So dilution is a key factor. The carbon content can be tougher, especially when you're dealing with carbon steels that have a higher carbon content. Sometimes that is not so important that you bring it down to that 030 max, carbon max. And that's always the question. Can you live with that? Can the end user live with that? And is it acceptable to have higher levels of chrome and nickel than 4304L? So, but most often our weld overlays will have a minimum of 2 weld layers and often 3. So in the case below, if you really wanted 304L on the surface layer and you didn't want the carbon higher than the 030 max and you wanted the chrome nickel to be in spec, you would do a second layer with 308L after calculating the chemistries out, depending on the dilution of the first layer. If you wanted 316L, you would actually start with a 309L MO filler metal because 316L has 2.0% minimum molybdenum. So you got to make sure that you get the higher molybdenum content in that first layer, the transition layer. So let's talk about processes, and we'll continue on with the dilution discussion with the different processes here. This chart shows a lot of information here, actually, which you need to study in depth. But basically, we're talking about the deposit thickness of a typical weld for overlay with different processes, the deposition rate, which of course for economics of production is very important. There's the dilution, which we talked about, deposit efficiency, how much you get. That again is an economic factor. And of course, you know, the consumable material used there. So if we take gas tungsten arc welding or TIG welding, you don't get a really thick deposit. You don't get a high deposition rate. It's relatively slow, as we all know, but you do get low dilution, or at least you can get low dilution. And that's one of the factors to consider, that if you can do it in 1 layer or 2 layer with having low dilution, you can be more economical that way. If we take gas metal arc welding, and of course there's many different variations of that too, you get a little thicker deposit, you get much higher deposition rates, but you get higher dilution. And you can see when it says 10 to 30% dilution, that the dilution, you have to be very careful, because the welder might say, well, I can do it faster. I'll turn up the amperage on that, or the wire speed on that, and to get it faster. But if he does that, he will get a higher dilution amount. I'll leave flux core for a moment, but the subarc is a common way of doing weld overlays. It can be semi-automated. There you do get high deposition rates, but you also get high dilution rates. there. So, but you get also a thicker weld deposit, which often is an advantage. So sub-arc welding is often used for weld overlays. There's also laser and plasma. I'll talk about those very shortly. But stick welding or shielded metal arc welding is also very useful. And again, you get good deposit thickness, not so great deposition rates normally. Again, highly variable in the dilution, up to 30% dilution. And the deposit efficiency is low, but it is good for small jobs. So this job is, or this chart shows different processes and the deposition rates. And if you're doing a large job, of course, the sub-arc is very effective. But if you use the sub-arc double wire process, you can get even higher deposition rates out of that, and probably without much change in the dilution there. So the and the bottom ones are actually strip cladding, and we're going to discuss that separately. So the advantages and disadvantages of each, and we've already talked a little bit about this, so I'm not going to go into detail here, but one of the reasons flux core is not used so much in weld overlay is that you have an issue of slag removal. Sometimes that's not easy. If you're doing several layers, you have to really make sure that the slag is carefully removed. The laser has expensive equipment to set up. It works well. You get low dilution, but it's very specialized equipment is used. And same with the plasma transfer. It's not easy to do. There are some specialist companies that do use these processes. But I'll leave that chart as part of the presentation, and you can go over it when you're looking for how to do a particular job. Let's talk about a few other issues here. One is there can be differences between the weld metal and the wrought material, which may affect the performance. Of course, the chemistry is one of those things. It's sometimes different than the wrought material. So if somebody says, I want alloy, let's say C22, nickel as the CRA layer, the chemistry in that case is very similar, but it is a little bit different. Other alloys, it can be more different. But on the other hand, if you're welding two pieces of, let's say, C22 together and use the C22 filler metal, well, you already have it there. So usually that's not an issue. It can be an issue in a few very, very unusual cases, but it is something to check if somebody is asking for clad material of a certain alloy. You have a cast structure of a weld versus the wrought structure of a plate. Of course, same thing is true if you're welding two plates together. You have the weld and the wrought structure of the plate, but you have the weld that is the cast structure. Again, a few cases where that is significant. In austenitic stainless steels, you have a ferrite phase there, which is not present in the wrought material. And sometimes ferrite phase can be positive. One example is preventing polythionic stress corrosion cracking, which happens in the oil and gas industry a lot. So ferrite can be a benefit there over wrought material. And sometimes it's negative because ferrite will embrittle at high temperature, reduce the toughness or the ductility of the material at high temperature. Occasionally, there's cases where it affects corrosion, in which case, if you're welding two plates together, you use a low ferrite filler metal for that, and so that has to be considered here too. Usually, I would say in 90% of the applications, the presence of ferrite is really not important from a perspective of the performance of the clad in service. Of course, with weld overlay, you have high stresses in the welds and the adjacent base material that may or may not be of concern. And there may be a hard zone at the CRA base metal layer. So if you use 309, you can get a very thin area where you have some martensite present, and that may affect the properties if you're doing any severe forming operation of it, of the piece. It's just something to be aware of. That you can't assume that, okay, everything, I can just treat it like solid material. So the compatibility of the filler metal against the backing material, essentially it's a dissimilar metal weld. Austenitic stainless steels to carbon and alloy steels. You generally use 309L or 309 LMO, depending on what you want if you want the molybdenum there. Occasionally, you might use a nickel alloy for that, even if you want a stainless steel there, because the nickel alloy does not form that martensitic layer usually. The 309L, 309 LMO has a fairly high ferrite content, which I'm sure you're well of from the Weld deposit. It's there to give better hot cracking resistance because carbon steels often have higher sulfur, phosphorus content than stainless steels. So that's a benefit. But you really need to, as welding engineers, to calculate the expected ferrite content based on the actual chemical analysis, not the typical. You don't want to use that. You want to use the actual chemical analysis of the base of the backing material and the filler metal. So you have to make sure you get the actual analysis for those. And then you have to estimate the amount of dilution. And what most people will do is saying, let's say you're doing it with gas metal arc welding, which has a wide range. You might say, okay, with the amperage that I specify in my WPS, it'll be 15% dilution, but you might want to look at both 10 and 20% dilution, sort of extremes there, to see whether you're covered just in case something happens where we're on the night shift when nobody is looking and the welder wants to get it done quickly. The high carbon base materials, for example, the 1040 carbon steel with 0.4% carbon, even with the 309L, it can result in too low ferrite and hot cracking. For nickel alloys to carbon and alloy steels, generally you don't need a special intermediate layer, first layer there. You most often use the nickel alloy that you're working with. There are exceptions to the rule, as there are as we all know, in welding. So the nickel copper alloys, you do need an intermediate, we sometimes call it a butter layer, perhaps pure nickel, perhaps another nickel copper alloy that's there. And that information is in the literature, what to do there. Now, alloy 625, nickel chrome moly 3 or ER nickel chrome moly 3 is really the most common nickel alloy used for corrosion resistant overlays. It's relatively easily applied, readily available, and of the nickel chrome moly alloys, it is really the lowest cost there. So it is used extensively for weld overlays. So you have to be very careful about too high heat inputs. I remember a case where a fellow in Canada used did an overlay with 625. He used the submerged arc process. He had a flux that welded beautifully, but it gave hot cracks. With subarc welding, you really want to do a lot of high production there, and the cracks didn't open immediately. So you do your layer, you examine it. There are no cracks there, but cracks will form later as the stresses relieve themselves. And he had to do the whole job over again. So yes, 625 is common. It's relatively easy to use, but you have to be very, very, very careful with high heat input. You want to keep it as low as practical for that. And the other thing was 625. Let's say you wanted the customer you wanted a like a 6% moly overlay. Well, there is no filler metal, or there's no matching filler metal for the 6 moly alloys, the 254 SMO, AL6XN type materials. They are welded with 625 or one of the C alloys, but you can use 625 to get the same corrosion resistance there. So 625 is commonly used even when you don't need the 625 corrosion resistance there. So heat treatment, and I saw there was a question in the chat already, or in the Q&A already about this. You don't need any sort of heat treatment usually for the stainless steel or the nickel alloy, but you may need it by code purposes for the backing material. And it's often a stress relief kind of material, especially when it's for oil and gas, or maybe when you have hydrogen sulfide there. So often it is done after the first pass is completed. So you do one pass, and then you do the stress relief, and then you do the other 1 or 2 passes after that of weld overlay. You don't need to do a heat treatment by code after that. And simply put, the stainless steel nickel alloys, wouldn't normally heat treat them if you were welding solid pieces. So therefore, you don't need to do it after the final welding. For the stainless steel nickel alloys, you may need to do it for the backing material, the carbon, chromoly, whatever steel underneath. When you do have to do that on the whole piece, you have to choose an appropriate temperature suitable for both the corrosion resistant alloy layer and the backing material. That can be a challenge in many cases, and sometimes it is a compromised temperature that is what is best for the corrosion resistant layer. And since you're using that for your corrosion resistance, sometimes you may want to ensure by doing a corrosion test that you have the corrosion resistance expected. And that actually is something that the engineering company who's behind the project needs to think about and specify if they want it. If you're a fabricator and nothing is specified, you would just do it perhaps and not think about it. It's something for the engineering company or the end user who is involved with it to specify. So I'm going to take an example of a nickel alloy overlay on a tube sheet. They wanted a pure nickel. They're going to use nickel 200 or alloy 200 for let's say the tubes. You want the tube sheet to have that weld overlay on it, and so you use either the ENI-1 or the ERNI-1, which is really the filler metal that you use for welding the alloy nickel alloy 200 there. So the Filler metals contain less nickel, 92 and 93%, than the wrought material. But again, if you were welding alloy 200 to itself, you'd be using these things. So obviously this is acceptable. What welding process will be used? That will determine an appropriate dilution for each weld pass. So if we assume 15% dilution of base metal into the metal overlay, and we'll again assume the carbon steel is 100% iron. The first pass, 15% dilution means 15% iron goes into the base metal. There's a little iron in the, 15% iron from the base metal into the weld overlay, but there's also a little iron in the filler metal, small amount, but 0.4%. So you have 15.4% in the first pass. That would be generally considered unacceptable. In the second pass, you have 15% of the first pass in there, and then the little bit from the weld wire, and you have 2.7% iron. So perhaps you can get away with that, and we'll come back to that shortly. Some people may want a third pass. You get only 0.8% iron in the third pass. So you have to say what level of iron is acceptable for that particular job. If it's caustic service, normally 2 or 3% iron will be acceptable. If you can guarantee 15% dilution, well, then a 2-pass weld should be acceptable. But if you're not sure that you're going to get 15%, it could be higher. You really need to think about that. And because if the end customer then goes and does a analysis of the top layer there, and he finds that it's actually 5% iron, he may reject it, and you may have to start all over again. Some end users will specify a 3 millimeter thick layer of the weld overlay that meets that composition requirement. And so sometimes you need to do a higher dilution process to get that thickness, as we saw from the earlier slides. So 3-pass weld overlays are actually fairly common when it's a very severe service. Going to briefly talk about strip cladding here. So instead of wire, you're using a strip. Typically, it's 0.5 millimeter thick and 60 millimeter wide. Wider strip is available. There's really 2 main processes. One is submerged arc and one is electroslag. The subarc welding is like using the wire subarc, but using a strip. The electroslag welding, it's a special flux that's high in fluoride, electrically conductive, and you get very, very high deposition rates with that. So the advantages are high deposition rates with low dilution, clean and smooth surface. A weld overlay done by wire, it will be rippled, and sometimes that needs to be machined smooth if in certain cases anyhow. Less distortion, you get a deep weld penetration, minimal fumes. However, strip cladding is only for the flat position. It's best for long, straight seams, and you can use it in rotatable. If you can rotate the vessel or a pipe, it's large enough, you can do that. You can use it, but otherwise, it has to be flat position. As in most methods that use flux, they can pick up moisture, and you need special equipment. So this is comparing the 2 methods of strip cladding. The submerged arc one has a higher dilution rate than the electroslag welding. The deposition rate is higher for electroslag welding. Travel speeds are just typical there. You can do some very high speed ones. Slag removal is easier on the electroslag. The quality of weld metal, they're both pretty good. The electroslag is slightly better. Penetration rate, and which relates to dilution too, as you can see, and the currents, the electroslag, you can get some very high currents there. And this is just a picture of a large vessel being clad. The vessel is being rotated so that cladding is done in the flat position. And you can imagine that maybe some very, very large fabrication shops can have this equipment. It's often done by a specialist weld cladding company instead, because the expense of the equipment and also the knowledge, the know-how, how to do this. Just taking one example here of weld overlay of carbon steel with the 2205 duplex stainless steel using the standard filler metal 2209. And this compares if the post-weld heat treatment is required versus not required. So if it's not required, you do 3 weld passes of 2209 and you get the 2209 composition on that third pass. 2209 can be used as the butter pass, that first layer, for that case, because it is suitable for the carbon steel, but you don't want to do the heat treatment on it. If a post-weld heat treatment is required, you do a first pass with 309L, then you do the post-weld heat treatment. That works well. It doesn't deteriorate the properties of the 309L. Then you do 2 passes of 2209 on top of that. The top deposit is again equivalent to the 2209. If you use the ESR process, you can actually do it with 2 passes there because of the low dilution content. So there are some advantages of using the ESR process, even though it is more expensive. But you could in doing it, but it can actually save cost in the long run. Finally, just a few comments about the inspection, and you all are in the welding business. So you're familiar with the problems that can arise during welding, porosity, and can occur if the welding isn't done properly, or if the base metals are not properly cleaned, or contamination of the gas mixture. Where there is a flux, slag inclusions, you don't want them in the weld overlay layer. Oxide inclusions, it's mostly about nickel alloys, but you have to be very careful, more careful with nickel alloys than with stainless steels in this regard, in the cleaning between passes. Solidification, cracking, and again with the nickel alloys it can be tricky because the cracks may not form immediately, and you have to use you have to be very careful there. And micro fissuring, again, it's making sure everything is clean. And there are some issues with grain size on certain of the high temperature alloys. Inspection techniques, well, that's no different than if you're doing a normal weld, you know, visual. If it doesn't look good, if it looks very rough, looks very dark in color, you know, you need to almost start all over again and get it right the first time. Radiography, ultrasonics can be used, dye penetrant, especially for the smaller surface discontinuities. And often it's done between weld passes to ensure that there is no micro cracks there, micro fissuring there. Often a sample, we call it a boat sample, you do with a grinding wheel, take out a sample to check the chemistry of the final layer, and then you can weld overlay back on top of it to bring it back there. That is often done. Hardness check can be done, especially on the first layer, to make sure that you haven't got any embrittlement there, and other tests as required by the application. So in conclusion, weld overlay is one method of cladding a lower cost material with a corrosion resistant stainless steel. There are other ways to do it. So, but there are many advantages to doing it. You do it often in the fabrication shop or a specialist firm that is set up to do it with some of the more specialized equipment. And I want to emphasize that really for the welding engineer, he has to be very, very thorough and careful in considering all the factors that are involved in making sure you get a high quality weld overlay there that has the mechanical properties and the corrosion resistant properties that the end user wants. And that applies even to other methods of cladding too. It is really an extra step that has to be done over using solid material. So in the end, you have to then also look at the total cost of doing all this, the inspection and everything. And in some cases, it can be just as easy to say, well, it's simpler if we use solid material. But of course, if it's very thick material, often you want to use the weld overlay cladding. So I will take some questions now.
There are few questions in Q&A. I request if you can read it or shall I read it?
Yeah, just oh, there's a Q&A. Yes, thank you. No, I can look at them here. So the first one is in sour service. Do we need post-weld heat treatment for cladded overlay material weld joint? In the particular case, it's 28 millimeter X65 pipeline steel with a 5 millimeter 625 overlay. What is the post-weld heat treatment temperature? I would have to look that up, but generally I would say yes. That's when you get into those kind of thicknesses, as far as I know, with most materials, you really do want to do the post-weld heat treatment, and you usually want to do it on after the first layer. Now with 625, you can actually do it as the final one too. It's very was not sensitive to the post-weld heat treatment for shorter periods of time. I'd have to look up the weld temperature there because it'll be really, it's for the X65, it isn't for the 625, and I'm not sure what it is for the X65 material. For hot tapping in sour service, we cannot perform post-weld heat treatment, right, and use the tempered bead technique for welding. Do we recommend a stress corrosion cracking test to be conducted for sour service with 85 ppm hydrogen sulfide? I would hate to offer an opinion on that, to be honest. We are very concerned about stress corrosion cracking, and you'd really have to look at this. But yeah, no, when you're doing hot tapping, you can't do the post-weld heat treatment. You use the tempered bead. It's a very specialized technique that works most of the time. But I'm no expert on that, so I won't venture an opinion. But 85 ppm H2S is not so high, but it's not that low either. So maybe a test is advisable. Oh, okay. So the next question is just about contacting me, and we will be getting a copy of the questions there. But yeah, you can contact me directly. My email is G as in Gary, Coates, COATES, at nickelinstitute.org. We also offer a technical service function and where you can go on our website and ask the question directly there also. Okay, next one. We are using a submerged arc cladding process for Inconel 600 weld overlay in some of the nuclear weld programs. Issues we are facing is lack of fusion or slag inclusion at the edge of the strip cladded weld bead. Yeah, okay. Even though we are taking utmost care so that the bead wetting angle and proper height, still such defects would come. I don't think magnetic stirring device would help here. I agree with that. Achieve defect-free weld. Strip weld, and I'm no expert on strip welding either in terms of doing that, but yeah, there are techniques to avoid those slag inclusions. Either the manufacturer of the equipment or the company doing it does have experience, but there are also differences in the quality. I'll say quality, but that may not be the right word, of the flux used. And some fluxes are released much easier. They don't do that. So I might even think of I might try a different flux. And I'll be honest here, often the purchasing people will buy the least expensive flux that meets the purpose and may not weld as nicely and can give problems where a higher quality, more expensive flux actually will give less problems here. So you really need to talk to the flux suppliers too to make sure that you have the best flux for that application. Next question was why annealing is not required in explosion cladded. Well, the reason is that there is no heat or I should say a very, very minimal amount of heat involved. So with roll cladding or weld overlay, well, let's say with the other way of cladding, the roll clad there, you're actually exposing it to very, very high temperatures for time, so you must do an annealing afterwards. But explosion clad, you don't need to do an annealing, but you really need to do a stress relief because you are putting a lot of stresses into that material. What about distortion and weld overlay case? Yeah, well, that's if you do you can't weld overlay let's say a 3 millimeter thick piece of plate without getting distortion. But yeah, you obviously you want to reduce the amount of heat input going into it on thinner material, but yes, you may need to straighten it out afterwards. Not so difficult with a flat piece. If you got a formed piece, that could be difficult, but yeah, distortion is a potential issue on thinner sections there, and just like it is when you're welding two pieces of plate together, distortion can be an issue there. How can we achieve E410 weld metal chemistry to meet 410 clad and base metal 5/16, 60 or 70 required height of WOL weld overlay, I guess, is the 6 millimeter. That is tough. That is tough. I'd have to think about how to do that. I mean, welding 410 is I presume it's a 410 where you're not looking for a high hardness. You're just looking for a 11-12% chromium content in the overlay there. uh, I've never come across it when it's done that way. I'll have to think about it. You might want to use. Yeah, I'll have to think about that one. That's a very unusual one. Yeah, I don't know about the total thickness there.
I think there are some Q&A questions are there, if you can answer.
Okay, which weld consumable shall use for 304H to 430 cladding? Whenever you do dissimilar metal, you really have to look at what property you need in the weld. But normally you 304H has good mechanical properties, good strength at the higher temperature. The 430 does not. So it may depend on the temperature. 430 you don't want to use at a very high temperature. So my first suggestion would be to look at 309L for that particular combination there. Yeah, you really have to look at the application, but because 430 embrittles well, really starts to embrittle above 300 Celsius, maybe that's okay, but the 309L would likely be the one I would look at first anyhow. How ferrite in austenitic stainless steel will prevent polythenic corrosion as it happens during shutdown and prevented by nitrogen purging? Yeah, so there are different ways of preventing polythenic stress corrosion cracking, and most petrochemical companies, they do take care when they do the shutdown by doing a nitrogen purging or soda ash washing. But the ferrite content in the austenitic stainless steel actually prevents, or at least it reduces the risk of polythenic stress corrosion cracking. So it is a common technique used for small parts in petrochemical, and it has to do with, of course, the ferrite content there. The cracks go through the austenite, but somehow the ferrite seems to protect it. I'd have to go back to the theory of that, but it is certainly a weld overlay is less likely to crack. Let me see now.
I think we can conclude, Mr. Gary.
Okay, yeah, sure. Yeah, there's a lot more questions, and so we'll get to those in due course. Yeah.
Okay. Thank you for giving the wonderful highlights on the weld overlay on ferrous and non-ferrous. I thank on behalf of Mumbai branch, today's speaker and the sponsor and participants, everybody. Thank you. We will meet once again in future. Thank you all.
Thank you
Well,
all
thank you.
very much.
Thank you, sir. I will send you the detailed question answers by email to you on Monday. From the system, I will come to know all the list. I will share it to you.
Excellent.
Great. Thanks.
Thank you all.
Thank you, sir. Participants, thank you for listening these wonderful sections. If you have questions, just you can send it to me or you can contact Mr. Gary sir directly. So they will reply to you. Okay, sir. Thank you.
Okay,
Good night.
thank you all.
Yeah.
Thank you, sir.
Right.
Saurabh, thank you.
Thank you, sir. Thank you to all.
Well,